Our last talk for the day will be by Emma Bailey, who will speak on large deviations in Selberg's theorem. It will be a Blackboard talk.
Yay!
That's much too much pressure. Please do not clap yet. Yes, it's a pleasure to be invited to speak today. As Louis-Pierre did, let me just give you a very brief history so you can contextualize the work I'm going to produce to you today. So I come from random matrix theory originally, but this work clearly has a very strong number theoretic angle to it. So this is just to temper your expectations on my number theoretic knowledge, yes, today. But to business. So I'm going to be talking today. Oh, please stop me if the writing is not big enough. So large deviations of Selberg's. Try and put this on. Selberg CLT. And before I forget, so the majority of this talk is going to be joint with Louis-Pierre. And then towards the end of the talk, I want to speak a little bit about some other work that I've done with Louis-Pierre and some other students. So let me name check them now before I forget. But that'll be towards the end of the talk. Okay, so we've seen quite a few, foreshadowings of what I'm about to talk about today. But let me be slightly more precise. So let's recall the central object here. So Selberg's CRT. Is this big enough? Some like nods, yeah, towards the back of the room nods. Excellent, good. So Selberg's CRT tells us that if we look at the log of the magnitude of zeta, let me try to be consistent with Louis-Pierre's notation. So if I take a uniformly drawn tau, so this will be my tau, provided I normalize correctly by half log t. So I'm left-handed, so I'm cutting off this side of the room. This should tend to a Gaussian. Okay, so in other words, we have, okay, let me just restate that. So the probability that log of zeta, again, uniform probability measure, equivalently some sort of normalized Lebesgue measure. Probability that log of zeta lies higher, say, than some v times sigma t, where sigma t is going to be, well, sigma squared t is exactly the Selberg variance. So provided I normalize by the square root of the standard deviation, this should certainly converge to the Gaussian CDF. So this should look like, right, I'm not telling you anything groundbreaking yet. This should go to the Gaussian CDF. So we know how this behaves for at large points. So okay, I should really emphasize here, I'm taking some real number v. So using standard Gaussian tail bounds here, this is like so we see this sort of Gaussian eta minus v squared decay, and additionally we get like a 1 over v. So standard Gaussian tail bounds happening here. So okay, I want to talk about large deviations to this. What does this mean? So our sort of key question is what happens when v depends on t. I typically v growing with t. So okay, as a sketch, so I want to be looking into these tails, the probability that I'm much bigger than is typical, so beyond the range of the standard, the central limit theorem here. Okay, so some history. Right, well, okay, so clearly let's start the picture off by what we know. So V, okay, so order 1 in T, so real V. This is obviously Selberg, and that's going to give us a bound. Let me just be crude. Certainly, I get the upper bound 1 over V e to the minus B squared. In fact, you can push Selberg's proof a little bit, so you can allow V to very slowly grow at T. So let's say V growing no faster than something like triple log T, the square root of triple log T, just shy of that. This is V, but growing very slowly with T. And again, you attribute that to Selberg, and you get the same sort of bound. Okay, so the next sort of jump here is we can now take V growing sort of exponentially larger, so log T, but we have to take some power of it. So this power is just shy of a 10th here. And this is due to Maxine Radziwill. And again, you get a bound, e to minus B squared, the Gaussian bound. There was subsequently work of Inu, who pushed this experiment up slightly. So this is log T to the 6th. Yeah, so it's gone slightly from a 10th to a 6th. And yes, again, you can get this bound. Okay, but for reasons which hopefully I'll communicate to you soon, we're actually going to be very interested in when this right-hand side here is on the scale log T. So since sigma of T is order square root log T, we ideally want to take our points V on the same scale as the standard deviation, i.e. look into the tail like square root log T. You'll see these are shy of a half here. So I want to go up to a half. Okay. First physical act. Let me try this. Good. Okay. I can still reach that. Good. Okay. Right. So if we jump to that level, so if we take V, okay, I'm going to be slightly imprecise here, so forgive me. I'm talking sort of about theorems which are much more specific than the results I'm just going to frame here. But if you take V up to log T, then in Sound's proof of the upper bound and the moments, you get a bound that's like log T to the little o of 1 e to the minus B squared. Okay, so right, we still get the Gaussian bound. Okay, let's just say this is generally on RH for general levels V. So you get the Gaussian bound, but now what we're missing is this 1 over V factor here. Okay, and Sound's work also allows you to handle. Okay, again, there's more ranges than I'm saying here, and I'm being very precise by what I mean exactly by these growths here, but let me just say, so Sound's result allows you to take larger V and you get some sort of exponential bound, maybe something like e to the minus C V. I think that's right. Good. And then, as you may expect, if you follow the work on the upper bound of the moments, Harper's result allows you, again, V up to square root log T, allows you to remove this here. So this is the source of the plus epsilon in the bound of the moments. So Harper's bound allows you to remove this. But you'll notice what we're still missing is this 1 over V. yeah, just to be really, really precise by what I mean. So if Selberg held at V growing like, I don't know, something like K log K root. So if Selberg held at this level, then we get the probability that log of zeta at this uniformly randomly drawn height tau higher than, okay, so be slightly careful about coefficients here. I'll comment on this in a second. Right, so if we rectify if v grows like k log t, then alpha is probably something like k times root 2 or something. I'm just trying to protect myself from forgetting about constants when I compare to it. So you have some alpha here, some let's say alpha positive. So this would apply. So if Selberg held here, then I would get a Gaussian tail, and this should decay like 1 over square root log t e to minus alpha squared log t. That's the equivalent way of saying it before. Okay, and there's actually a conjecture of Radziwill dealing exactly with this situation. Right, so conjecture the conjecture of Radziwill says the following. So if alpha is positive, then what we expect is that the probability that log of zeta lying at some level that's growing like the variance now rather than like the standard deviation, this should be like, okay, I should go to C alpha over, let me try and get this constant right now. I think something like alpha to log t minus squared over 2 du. Right, so it's almost Gaussian. So the conjecture is, right, this part here is Gaussian, but you have this factor here. So if C alpha is not 1, then we've got something that's happening slightly different here. And he, yes?
So what does the arrow sign mean here? Because there's T also on the right hand side.
So yeah, I mean that as T gets large.
There is a T on the right hand side.
There's a T here.
Does it mean that something converges to something that you can?
That's, you mean asymptotic, right?
Yeah, sorry, I mean asymptotic, thank you. Yes. Grows like.
Okay.
Thank you. Good. So yeah, the conjecture is this, and further conjectures. Let me do it in a nice color, where C alpha is the coefficient of the 2 alphas moment of zeta. Not zeta factorial, zeta. Okay, so we're getting moment coefficients coming into the large deviations. So I want to spend a few minutes trying to convince you why maybe you should expect this, or maybe why you shouldn't be so surprised maybe that these are appearing, as at least I was when I first saw conjecture like this. Okay, so just as a very brief reminder, we saw exactly that. Maybe just be a bit more exact. So what is C alpha? So if we take the 2 alpha moments and we normalize by the leading order in alpha, then we should go to C alpha as t goes to infinity, where C alpha is, as we saw yesterday, written as, okay, apologies for my bad notation here, A sub alpha, F sub alpha, where we have what's known as an arithmetic part, multiplied by what's known as the random matrix part. So, okay, since I'm in the spirit of being very explicit, So A sub k is going to be like some Euler product. Okay, maybe don't actually quote me on this. This is liable to be slightly off. With that side of the room can't fact check me at the moment, because you probably can't see that. So AK is just like some Euler product. We saw, okay, there's a different expression in terms of divisor sums. So yesterday, but this is equivalent, at least for integer k. And then the f sub k is this random matrix branch G function, the ratio of branch G function. Okay, right. So let me try and convince you that maybe this isn't so wild. So in this paper where Max conjectured this statement, he proved the following. So in Selberg's work, he showed that you essentially can boil the central limit theorem, the proving the central limit theorem, down to a question on Dirichlet polynomials. So obviously you can ask a question about large deviations of Dirichlet polynomials, which is what Max was considering. So let's have a cutoff x and look at 1 over p half plus I tau, and ask the probability that this is greater than, okay, we'll use sigma, let me use no sigma hat. Okay, I'll try and be careful with my coefficients here. Okay, the presence of the root 2 really is just to cancel the half in the Selberg variance. So right, this should somehow approximate zeta log zeta. So x here he takes is some just shy of t. So x is something like t to the 1 over probably log t pat squared, just shy of t.
Is it the modulus of that sum?
Maybe the real part. And this sigma is just the variance of this. So again, by Mertens, this should grow like half log x. This is just whatever the standard deviation. And prove that this again goes to, okay, we've got some alpha here. Alpha to log t minus u squared du. Okay, I really should be careful here. This is not, it isn't exactly find the moment coefficient, find some other coefficient, but shows that this coefficient c tilde of alpha is strictly positive and is not 1. Okay, so in this field, what else could it be other than the moment coefficient? So that's, I guess, a justification 1. Justification 2 sort of follows from what we saw from Sam's talk yesterday, which is that you can, when trying to estimate the moments of the Riemann zeta function, you want to, or you might want to write them in terms of the measure of high points. So the moments of zeta, as conjectured, have obviously this as its leading order coefficient, so it must come from somewhere. And in Sam's work, he shows that the biggest contribution to the 2 alpha at the moment comes from points exactly at this height. So it's the most natural, maybe, that the coefficient should come from large deviations at that height. That's sort of motivation 1, perhaps. Motivation 2. So motivation 2, okay, is currently not secretive, but you have to wait to the end of the talk. So motivation, perhaps I didn't header this motivation over here. Let me do that. This is motivation 1. Motivation 2 is some numerics, which I'm hopefully going to have time to present at the end. So you have to hold your horses for that one. Okay, so let me maybe move to motivation 3. Well, okay, so let me just sketch out in words. So maybe one way you can see this, we can actually define a tilted measure. So you can slightly tilt this measure doing a standard exponential tilt, which is actually related to the GMC stuff we saw this morning. So, okay, here come the stream of conjectures. If you assume RH, if you assume the moment conjecture, if you assume that, so Vasari has some very nice results proving that essentially zeta weighted, log of zeta weighted by exactly what I'm sort of hand waving around is still Gaussian, at least for weighting by low moments. So if you assume all of that, then bounds like this pop out. So just to sketch this, that was really just in words. So you can do, let's do an exponential tilt of this measure. And then if you assume, I guess, like RH, moments, extrapolate some works of Vasari, then you're left with something like this. That was hand wavy, but I'm happy to chat later a bit more about this. But the fourth motivation I want to discuss, because it's very much in the theme of this conference, is tying it back to random matrix theory. So motivation 4 is from random matrix theory. Okay, so recall we saw probably yesterday that so if we take a unitary matrix A that's drawn randomly with Haar measure, so it's uniformly distributed effectively. So if we do that, right, here we go. Can I pull this down? Yes. Not quite. Okay, so if we've got our random matrix here, then we've seen already that by the work of Keating and Snaith, they showed that the log of the magnitude of the characteristic polynomial at A, of A, again normalized appropriately, in normalization is half log n. This again goes to a Gaussian with large matrix size. So entirely, you can ask the same question. You can say, okay, I want to do large deviations of this central limit theorem. So they started being done about 20 years ago. So large deviations of the Keating-Snaith central limit theorem, say, started by work of Hughes, Keating, and O'Connell. They used the principle of large deviation principle, proved a large deviation principle for the log of the characteristic polynomial at both moderate deviations and large deviations. So don't worry if that's a bit opaque, that's fine. But for example, an example of what they showed, there's a specialism of a much wider, more powerful result. They showed effectively that the log of the probability, that the log, so this now is Haar measure, that log of the characteristic polynomial being greater than some, say, C log n, so exactly in the same range for C positive, this goes as n gets large, or okay, no, I should say this behaves asymptotically as n gets large as minus C squared log n. So hope you can see in the same vein, this is giving like a Gaussian tail here. If you can't fully exponentiate both sides because you're losing stuff at the head here, possibly. But this is showing a Gaussian type tail. But you can actually be even more precise than this. So in fact, you can prove the following. So this is work of Fourier, Meniel, prove the following. So again, draw your matrix randomly, and then not the log, but you can actually explicitly describe this probability. That's A greater than C, or no, okay, I can deal with C as a constant. For C positive, this is let's see, square root 2 log n. This 2 again is just to cancel the half in the variance of the log characteristic polynomial. And I've left the fraction blank because they proved exactly that this has, okay, so terrible notation, but this is a Gaussian shifted, but shifted just by the random matrix part, which I think I've covered up. Yeah, good. So this right here. So again, more evidence that maybe this is what's happening. So I think it's time for me to tell you what we can show. So I'm going to flip back to alpha here. For alpha greater than 0, okay, again, tau, as always, is uniform. We can show probability log of zeta I tau alpha log t. This is bounded by something like log t eta minus alpha squared log t. Oh, sorry, I should be careful. Thank you, RP. Not quite. Okay, so we have a restriction on alpha. I'll explain that in a second. Okay, so what's the positives here? Right. So what we're gaining here is this factor. This is what's new. This factor here. So I've emphasized that there's some implicit constant that we're losing here depending on alpha. We'll certainly have a 1 over alpha from this guy inverting the level of the large deviation. Fine. But from what I've just tried to convey heuristically, you should also be seeing the moment coefficient here. How to get it? Okay, that's a different question, but that's what we should expect to see popping out here as well. Okay, so some comments here. So our theorem is unconditional, so it doesn't require the Riemann hypothesis. And that's exactly why we've restricted to alpha strictly less than 2. So as hopefully we saw, we did see very clearly in Sam's talk that the points at this level, at level alpha log of t, they're exactly the biggest contributors to the 2 alpha moment. So alpha being less than 2 is sort of, you're getting the same information as up to the 4th moment here. And we actually need to use the 4th moment in our proof. So we actually need to be strictly shy of 4 here, or of 2. So in theory, you could push this bound higher. You could let alpha be bigger than 2 at the expense of assuming RH. But okay, should work out the details finally. But that should hold. The other side of it should just be an artifact of the proof, and hopefully will be removed in the near future. I'll leave it at that for the moment. Okay. Okay, that's all new. Let me do some erasing. So erase, are there any questions up to this point?
the C, is that the full coefficient of C alpha, or is that just?
That's the, so the conjecture is that, so this here is just something that you can prove is positive and not 1.
Okay, so it's not that C alpha.
It could be. No, so so it's not excluding, okay, maybe I should be careful here. Possibly this is only for alpha between 0 and 1. I should be careful, I should check that. Because there you know that the moment coefficient isn't 1. And so that's implying that something funny is happening. So another question?
Just a quick question in the random matrix case.
Yeah.
Is the constant there FC the moment constant as well?
Yes, sorry, yeah, maybe I wasn't clear. So yeah, that's exactly the non-arithmetic part. It's exactly this guy here, the coefficient of the 2cth moment. Apologies for my terrible notation there. Okay, so I really won't spend too much time discussing the proof of this statement because, oh, sorry, yes, thank you.
Is there an error term in that formula for the?
Oh, yes, it's probably, no, that, oh, sorry, maybe asymptotically. That's way nicer. Better? Good. Okay, did I want to leave that up? No, I didn't. Right, I'll just say a few words on how we prove this and how it differs from what we just heard in the previous talk. I want to focus for the rest of the talk on some nice corollaries we can get from this result. So, oh, I'm going to regret doing that. Some aspects of the proof. It's entirely inspired by the recursive method developed by Arguin, Bourgade, and Vasseville. So uses the recursive procedure developed by Arguin, Bourgade, and Vasseville, Louis-Pierre, Paul, and Max. Okay, so there are some slight differences here. So our implementation of this is actually slightly simpler. So if you're now very motivated to try and understand how these branching random walks fit into the picture, our implementation of it is at least slightly more, doesn't have as much technicalities involved as the original work. So maybe it's a good place to start. Slightly simpler, so in particular, there's no discretization, obviously. So when LP was just talking, he was talking about the FHK conjecture, which is conjecture at the maximum of zeta. And so your first step is often to discretize. Here, we're just at one point, so there's no discretization to start with. Also, our barriers, so these upper and lower barriers that Louis-Pierre was describing, so our barriers sort of become like checkpoints. So they're no longer necessarily, well, okay, our barriers are continuous, but we just don't require as much at every stage. So we need to, I'll say this informally, check our walks less severely. Okay, that's very hand wavy. But in order to get the precise, as Louis-Pierre very clearly explained, in order to get this precise extra sort of heavier tail, the y e to the minus 2y, you need to be very careful about not allowing too many walks through. So we don't have to be quite as careful in this implementation, but actually our barriers have to be a bit higher. So barriers, if you compare the two, you might notice that our barriers are a little bit wider, not too wide, that would be bad, but barriers are a bit wider. Okay. That's what I wanted to say. Okay, so let me just again be somewhat explicit. So RSK are exactly like same structure, as we just saw, p to minus I tau over root p. So before we had a p to IH here as well, so we don't have that. We're not doing a maximum, we're just doing it at one point. This is for tau uniformly. So again, this is the starting point, this is our walk, and this is what we need to eventually reach. So we want essentially ST to be, want probability, I want to be sort of handling the probability that our walk at t being like log t is higher than some point v for v essentially the order of alpha log t. These are now our high points. This is the equivalent to what LP was just describing with the high points. These are now sort of our high points here. You can do the same sort of decomposition in terms of good events and bad events and build yourself up. And again, the biggest contribution comes from the very last step. But I want to focus on some I think, a nice corollaries of this result. Okay, so should have time to detail 3 corollaries. So the first one is it was known at the point at which we proved it, but this is an alternative proof of this fact. So moments, say sharp upper bounds on moments with, okay. So sharp up and down moments between the 0th and the 4th moment. So, so a corollary of our result is the following. You look at the moments of zeta, so the beta dt, we can show this grows no faster than what we expect as the sharp bound. This certainly was known already. This was known first by Heap. That's Phil. Who actually, so their result, you can get the endpoints as well. This is unconditional. Unconditional sharp of bounds on the moments. Okay, so why is this a corollary? Well, I'll just very one-line sketch why is this a corollary, where we saw yesterday that effectively this is, be careful about your endpoints, but that's very handleable. This is effectively like a sort of measure of high points, or it's interval involving measures of high points. ADB, where SB is the probability or normalized Lebesgue measure of high points. Probably doesn't really matter. Tau is greater than V. V. Yeah. So equivalently, if you're from a chaos point of view, this might look like thick points as well. So that's another perspective here. And then, okay, so from Sound's lecture, Sound tells us that the main contribution is essentially levels V growing like okay, beta over 2 here, log t. You know, so this is exactly the range of our theorem. If beta is between 0 and 4, then beta over 2 is between 0 and 2. So, okay, you have to be careful. You have to actually formalize this, but more really that's how you show that. Okay, so on the theme of moments, so corollary 2, you can look at moments in short intervals. So again, this was partially known already, and partially it's an improvement on what was known. So let me state what we can prove. So if let's say theta is in 0, 3, you can take any beta, then see if I can get this right. Take a window growing like log t to some power of zeta r plus I t plus I h, 2 for the beta dh. This should grow no faster than, so depending on beta, actually, no, let me be more precise. This is less than equal than, maybe I do want to bound, let me be careful about my constants. Okay, I can take, so if I take, be a bit more precise here, if I take some, say some a greater than 1, then this should be less than a log t to the theta squared over 4 plus theta, probably here. That feels right. If I normalize by 1 over log theta, this should be like the short moments. So this is true for all t, except on a set of Lebesgue measure, well, possibly on a set of Lebesgue measure. So this was known already. This was work of Arguin, Guillemet, and Vasseville.
Less than t over a.
Or maybe normalized Lebesgue measure. Yeah, sorry, I'm using them equivalently. Yeah, so maybe formally I have a two. Thank you. Good. Okay, and to tie into what Adam was saying earlier, maybe I should write that down. So this was work of Arguin, Guillemet, and Vasseville. And actually, let me even make sure I don't make a mistake here, because I'm liable to. In fact, you can say a bit more if you're sort of above a critical temperature. So if beta is strictly greater than 2, 1 plus theta, so before I write anything more, let me just sort of localize you back to Adam's talk. This 2 is exactly his sort of critical 2 from earlier. So theta equals 0 is intervals of order 1. So the critical temperature there is 2. Then we get a sharper bound. This improves, so AOR consider this as well, but didn't get quite as sharp a bound. So we can show using this that write the full statement. Look at exactly the same thing. To beta, this is less than or equal than some constant CA beta, some positive constant, and you get the ratio. Okay, make sure I get my coefficients here right. 1 plus beta minus 1, and this should be like beta over 4 square root 1 plus theta. Good. That feels right. Yeah, that's right. And again, except on for all t, except before measure again. Right. Right, so okay, so let's just specialize very briefly to theta equals 0. This is like what Adam was talking about earlier. This is short intervals, so intervals of order 1. And then, so what's on top is the case. You have to move, so if beta equals 2 and theta equals 1. So Adam, from before, what we saw was like theta equals 0, beta at the critical temperature. So not, this is for strictly above, at the critical temperature, you saw like log t over square root, log t, these square root cancellations. This is again related to this chaos perspective. Okay, so let me now move to the third corollary. that we can prove, because this leads into the numerics, which I'll finish on. So a small amount of setup, but this is very related to what we just heard. So corollary 3, maxima in I affectionately refer to as short-ish intervals. It's not a very precise statement. Intervals. So I mean intervals that are growing exactly like this, growing like log t. Okay, so do I want to recall? Maybe I'll recall briefly the FHK conjecture. So we just saw that the FHK conjecture tells you that the maximum in windows of order 1 of the log of magnitude zeta for some uniformly drawn height tau, this should be like log t minus, okay, we get log correlations, we see this minus 3/4 log t. I'm going to be very imprecise about the fluctuating term, but this is the conjecture. But of course, so if you take yourself back to random matrix theory, there, as Sanders deduced, restricting to intervals of order 1 is very natural because we're on a circle. On the line here, maybe it's not so natural. Maybe we want to let our intervals grow. Actually, let me give some space here. Maybe I'll use this to compare, as Alpi introduced, to compare to the following. So say if Yj were IID Gaussians of some variance sigma squared m for some real number sigma here, then if I look at the maximum over, say, 2 to the j of these random variables, then this is the picture from branching random walks. This should be like 2 sigma squared 2 and minus 1/2 sigma squared over 2 sigma squared log 2 log n plus, okay, something else fluctuating. Okay, so these are just normalizations, so you can effectively ignore these bits. So in particular, if you set, say, the variance here, sigma squared, to be 1/2 log n, so 1/2 log 2, then this leading term becomes like log 2 to the n, and the sub-leading term becomes like minus 1/4 log n. You think this is a good choice of sigma. So the comparison here, so this is IID statistics, this is like the REM, if you're familiar with the random energy model, this is what you get in that case. And instead here you get a different answer because of the log correlation, as Alpi very clearly explained. So let me give you the conjecture and then what we can prove. Right, so conjecture in this case, just work of Arguin, you may, so you're allowed now to let your intervals grow a little bit. Okay, log zeta. This should be like, probably quite imprecise about the fluctuating term here. Triple log t. Okay, just for the sake of time, let me just capture the fluctuations in one sentence there. Okay, so this should be strikingly different. Well, not strikingly different, but somewhat different to what we had up here, right? So you see this quarter coming out versus what may be happening up here for FHK with 3/4. So what's happening? So we're looking on much wider intervals. So these, let me, if I can do a sketch here. So this is the critical line. So this is an interval of order, let's just use theta equals 1. of order log t, then we know that, well, in an interval of order 1, there are approximately log t zeros. So in an interval of order log t, there are about log t squared zeros. So we essentially have like log t shots at being tall. So in this interval, so we have log t squared points effectively. Now, if the interval is short, as Alfie was explaining, you're going to see these log correlations and they're going to dominate. However, now most of our points are not close together, right? Most of them, this is a much wider growing interval in t. So actually, you should not expect that the log correlation dominates. Instead, you should actually move to this random energy model, this independent structure, which is why you expect to see a 1/4 here rather than a 3/4. And why you should see this square root 1 plus theta, well, okay, just in one line here, well, it's exactly due to this counting argument. What's your entropy? How many points do you have? So the number of points in an interval log t to the theta is log t to the 1 plus theta, exactly like this discretization 0 argument. As you'll see, it's doing exactly the standard thing you do for doing maximum of IOD random variables. You need to cancel this entropy out, and it turns out that because you need to cancel this term, this is exactly the right term. From the Gaussian, this will get squared. That's sort of why that's appearing here.
Conjecture for all theta positive.
For all theta positive, thank you. Thank you very much. That's important. Yes. So this is for theta greater equal than 0. But this is clearly not sharp at theta equals 0, as we've seen already. It's a theta positive, exactly. Good. Okay, so the leading order of this was established in the same paper there. So they proved this is leading order. But as a corollary of our results, we're able to go up to order 1. That seemed to come after this. Let me use this. So what we can show, so I guess corollary 3, I suspect I've moved between Roman numerals and Arabic numerals. So corollary 3 is that, so for theta and naught 3, y positive, okay, we have to have some bound on y. You'll see why in a minute. Okay, and I've used the shorthand notation LP introduced, where t is, sorry, you probably can't see this, t is log. Capital T is just like the time in our walk here. So you have some restrictions on y, and I'll explain why that is in a minute. Okay, so the maximum, the probability, okay, we get an upper bound of the right side. So it is less than square root 1 plus theta. Okay, let me even use my notation from above. T 1/4 1 over square root 1 plus theta log t plus y, except, so for all t, except on a set of measure t, and I actually really want to emphasize this is important, so let me do it maybe in yellow. Okay, so our t from our Selberg measure, and then we get an exponential decay, and we also see the Gaussian decay. Oh, yes, yes. Sorry, yeah. So, yeah.
Okay, it's another letter, right?
Yes, probably. I've mixed up t's here somewhere. Yeah. So maybe let's call this n. It's all right. I should be precise. So this is n. This is n. This is n. Hopefully that fixes it.
So small. What is the small t now? It's m.
Oh, maybe this is log.
No, I'm so sorry.
It's all right. There's some duality going on. Yeah, maybe it's exactly the same. Morally, hopefully the answer.
It was two different.
Maybe it was two different things. Good. But what I want to emphasize here is this decay bound. So with the log correlation, we saw a y e to minus 2y. So we don't see that anymore because of the IID. But actually, we also see that this Gaussian. So for larger y, provided we're sort of less than this bound here, this Gaussian part is going to dominate. So if we could prove this for much larger y, that would have implications for very large values of zeta. We can't, but we can go up to this range. But for smaller y, this exponential tail dominates, as you see in the REM. Okay, so I really should talk about numerics now. So if you excuse me while maybe we get the slide down. Now there. Hope the suspense is worth it. Okay, so this is what you're about to see is one plot of some numerics that we did in a different project, so a related project certainly. Excellent. Good. Okay, so what do we see here? This is a plot trying to demonstrate this conjecture / now theorem in terms of the deterministic part. Along the bottom, we've got theta. So here, this is intervals of length order 1, and these are intervals of length order log t cubed here, and t is 10 to the 9. So there are people in the audience for which this is embarrassingly low. I make no apologies, I'm not an expert in numerics, but I'd be very interested to have conversations about people who know a lot about doing these numerics much higher. So we have to stop here because things are just slow. Okay, so I've taken thetas every quarter along here, and so for each sort of line here, so let's take this point here. So this is intervals of length order t. So what I've done is there's 300 green dots on each column. So each of those dots is the following. So you draw a height uniformly between 10 to the 9 and 2 times 10 to the 9. And then you look in a window around that point of length here, order log t, or minus log t to log t, here order 1, here order root t, etc. Then you discretize that interval according to the zero spacing. So we're going to have log t to the 1 plus theta points. And I just ask, what's the maximum in that interval? So I've got a discrete set, what is the maximum? And the maximum is plotted in green. And I repeat that 300 times, and that's each of those. So I said I should be saying we, that's what we did, but that's one would do. Okay, that's the green dots. So the red lines here is just connecting the mean of each of those here. And then the yellow line and the blue line are two different predictions. So I'll try to capture that at the bottom here.
How are you connecting the means?
How are we connecting the means? We just, how are we connecting the means between here? Maybe it's just linear interpolation between the two. How are we connecting the red line? I think it's just linear interpolation.
Yeah, it looks like a segment.
Yeah, I think it's just the line segment between the 2 points. That's all that is. Okay, so then the yellow line, which is shooting off, which is not matching the data as well, is okay with c equals 1, and what we mean by that is we're not using the Rassville conjecture for the large deviations of Selberg. So we're using the Gaussianity, but we're not changing by the moment coefficient. So you can see the yellow line is sort of shooting off and not matching the data as well, even though the variance, as we can very precisely conjecture, the variance actually is decreasing with theta. So instead of this blue line, what that means is we're incorporating the Rassville, sort of these deviations, the moment correction to the large deviations, and you can see hopefully the fit is at least much better than if you didn't have this correction. Okay, now, there's just some specifics on exactly, we can predict exactly what sort of Gumbel parameters you should get, and this moment coefficient f is c here is showing up in the shift in the gumball, the mean of the gumball. But I'll leave this up because I'd be interested to have some conversations about various aspects of this plot, how we can improve it. And you'll notice perhaps that we're slightly shooting out at the top there. So we have some theories, but I'd be interested to talk to people if they can explain what's happening for larger theta. But I will end there. Thank you very much.
Go closer to zero, the blue predictions actually are.
So it shouldn't match, right? At 0, we have log correlation. So that's why sort of it's included to emphasize something different is going on at 0. Actually, there's very interesting work of Louis-Pierre and Lisa Hartung and Guillaume Dubac, who created via a model of zeta, are able to do an interpolation between theta equals 0, interpolating upwards, interpolating between this -3/4 and -1/4. So it shouldn't match very well at the start. We know that, yeah.
Also about the graph, when theta gets close, when theta gets big, like 2, 2.5, 3, it seems less good. Is there a reason that you do
Yeah,
that?
okay. So that's sort of my question to the audience. I'll proffer my my guess at possibly what's happening, but back of the envelope calculations suggest this isn't the right answer. So an initial guess was that, okay, so we're correcting by the coefficient of the moments. So you can look, so, Heath-Brown computed, right, the full moments, the fourth moment of zeta, the full polynomial, and then there's some nice work of Conry, Farmer, Keating, Lewis, and Snaith that actually gives the full moments, like they actually numerically calculate the coefficients of like the log t to the 4 minus coefficient log t cubed, etc. And what you can observe from that is actually lower order coefficients can be quite large, and actually in order of magnitude large, and we're quite low down here. So actually maybe you need to factor those in. Back in the calculation, exactly, just the leading order coefficient.
There's a big gap.
Exactly, and then so obviously you need to normalize by like log t, effectively, if you're dividing by log t to the 4, or log t cubed by log t to the 4, you need to normalize by that, so that plays into the picture here. Back in the calculation suggested that wasn't the solution, but I'm very happy to correct it, or if anyone's got a better idea, also all ears. John.
I have an idea.
Good.
So the conjecture of Max's follows immediately from the moment conjecture, and as Sam showed, at this height on the critical line, which is pretty low, you get huge deviations from Gaussianity. So what we should really put in is the finite n. That's what you do.
We do, yeah, we do that.
Okay.
We prep for the variance, so we put in as much as we could. This is where we're at. I hope someone can do 10 to the 12, 10 to the 13, and it snaps back down. Brilliant. So it's a small t effect. Yeah, this is where we're at.
I have a question. So where is the restriction that theta should be less than 3?
Oh, thank you, I should mention that. Yeah, so that's exactly tied to the fact we need the fourth moment. So the leading order for this maximum is like square root 1 plus theta log t. And so that's the equivalent to which moment we need. We need the square root 1 plus theta log t. If you equate that to 4, that means theta has to be less than 3.
Let's thank Emma again.